Good afternoon, guys. If you guys can hear me, can you just type in yes? I'm not sure if you can really hear me. Oh, great. Thank you. We'll wait for a couple of minutes. I think we only have about 10 people, rather 7 people who have joined. We'll wait for a few minutes to see if there are more people coming in. And then we will get into coordination compounds. I guess we can start the lesson because it's 12:35 right now, and we will need some time to actually finish this topic. Now, you've already studied quantum mechanics and bonding in grade 11, so the first part of the lessons that we did were mostly a review of your grade 11 quantum mechanics, shapes of molecules and stuff. One of the things that you did study at that time was the types of bonds. We did study about, or rather you would have studied about ionic bonding, covalent bonding, and coordinate covalent bonding. Those are the 3 types of bonds that you should have studied. And coordination compounds are mostly based on the 3rd type. Now, what we have done is, in acid-base theories, we did talk about Lewis acids and bases. Or another way to look at coordination compounds would be interaction between Lewis acids and bases. So if you have an understanding of that, you can understand most of the concepts behind this. So what I kind of plan to do is we can identify complex or coordination compounds, define the central metal ion, ligands or multidentate ligands, explain the metal ligand bonding using Werners theory, mostly focusing on primary and secondary valencies, name some complex compounds, predict the geometries of complex ions, the general nature here. The second PowerPoint will give you a little bit more clear explanation about the bonding. Here we are going to look at the octahedral complexes, tetrahedral complexes, and the square planar complexes. Those are the 3 types of shapes that you would be seeing. And some isomers in complex compounds and the impact on the color of these complex compounds. And we can use crystal field theory to explain how these compounds exhibit different colors in aqueous solutions. Those are some of the things in the first PowerPoint that we will be doing. And if we have time, we will try to get into the second PowerPoint. That's the intent. Now, if you look at a complex, so here is an example. We have cobalt as a central metal, and it is bonded to a few ligands. Here, the 2 different ligands that you have is ammonia and chlorine. The formula of the compound is actually CONH34Cl2. And this is how you can name it. We will actually be looking at the names later. This is called tetraamine dichlorocobaltate 3 complex ion. You would notice that this is actually a negative complex ion. Whenever you see negative complex ions, the metals end in ATE. And the 3 here represents the oxidation state of cobalt. So this is a representation, structural representation of a complex with a name which we will be trying to name later. So the central metal atom bonded to groups of molecules or ions is mostly what we refer to as a metal complex. Usually these ions, when we write them, we can write them as a dissociated substance dissolved in water. Then we refer to it as a complex ion. Compounds containing multiple ligands and exceeding their normal combining capacity are these complex compounds. What we mean by that is cobalt with a 3+ oxidation state should have combined with just 3 negative ions. But in this case, you will find that it not only combines with chlorine, but also combines with ammonia, and whereby it exceeds its normal combining capacity. So you will find that in complex compounds, the ability for transition metals usually to form bonds which exceeds the normal combining capacity is a normal factor. And those are the molecules that we normally refer to as a complex compound. Here is an example. Here the potassium part is the positive part of the salt ionic compound. And then you have square brackets. These square brackets are also called the coordination sphere. Within that, you usually have a complex species. The complex species can be either negative or it can also be a positive complex species. In this case, the positive part is just a metal, potassium, but the negative part of the complex is actually a complex ion. So the square brackets usually indicates the coordination sphere. Cobalt is a central metal ion that actually forms the complex. And we have two ligands here. One is amine and the other is chlorine. Now there are 4 amines, therefore it's tetraamine, and 2 chlorines, therefore it's dichloro. The names slightly change when they are inside the coordination sphere. Here, if you count the numbers 4 plus 2, that is the number of ligands that are present in the complex, it is 6. So that's called the coordination number. Now, we will be starting to call this as a secondary valency, or the secondary valency is also called the coordination number. And the total number of ligands can be, we can have 6 different ligands, or we can have a single type of ligands, but totally there will be 6 of them. That's what we normally find within the coordination sphere, or 6 pairs of electrons will be coordinated to the central metal ion, whichever it is. So each of these ammonia molecules, as you already know, has a lone pair, and therefore that lone pair can be coordinated, and the cobalt provides the empty d orbital for the bonding process. We will see examples as we go along. The molecules or ions coordinating to the metal are usually called ligands. They could be anions, or they could be molecules or polar molecules. They are generally Lewis bases. So by definition, Lewis bases are electron-rich molecules. And Lewis acids are electron-deficient molecules. So the central metal ion usually has empty d orbitals, which is made available for coordination with the lone pairs that are present on the Lewis bases. That's how the bonding takes place here. Some common examples: water molecule is a very good ligand. It has got 2 lone pairs, even though only one of them is usually coordinated. It's called aqua when it becomes a ligand within a coordination sphere. NH3 is ammonia, but when it becomes a ligand within a coordination sphere, it's usually referred to as amine. Cl- is a chloride ion, and chloride ions, again, when it comes inside the coordination sphere, it becomes chloro. So namings, you may want to get familiar with that change in names for these common ions or molecules that we have. Cn- is cyanide, and when it becomes a ligand inside a coordination sphere, we call it as cyano. These are just 4 examples. There are more of it. So here I've taken an example of cobalt combining with ammonia and chlorine to form 3 different types of complex compounds. And the interesting aspect is, if you look at the color of all of these compounds, they are different. First one is hexamine cobalt 3 complex ion. A complex ion if it dissociates. So you have 6 coordination number, or 6 amines or ammonia molecules coordinated. Or within the coordination sphere, you have 6 ammonia molecules. So if you dissolve this in water, it's going to dissociate to give you 3 chloride ions. The chloride ions are not part of the complex. It's outside the coordination sphere. So if you look in the last column, it gives you 3 chloride ions per formula unit. There are 3 of them. And the complex molecule is a single unit of positive charge, so it will be 3 positive in this case. Therefore, the total number of ions per formula unit will be 4. That is the 3rd column. So if you look at the color of this compound, is orange in color. The second one is COH NH3 5Cl. So now inside the coordination sphere, you have 5 ammonia ligands and 1 chlorine. And if you look at the chloride ions that are present outside, that has decreased because the oxidation number of cobalt is 3 positive. When it comes within the coordination sphere, it satisfies two kinds of valencies, the primary as well as the secondary. So one of the positive charges are neutralized by that. At the same time, it's also donating a pair of electrons by forming a coordinate covalent bond. So we have 6 ligands, coordination number is maintained. But when you dissolve it in water, it produces 2 chloride ions, and total number of positive ions will be 1, and therefore you have 3 ions per formula unit. And the color is different. That's where we will have to explain later what causes this. If you go to examples 3 and 4, the formulas are exactly the same. The only difference is the position of the ligands around the central atom is slightly different. So you have CONH34Cl2 and CONH34Cl2. One of them is called a trans isomer and the other is called a cis isomer. So cis trans isomerism you may have come across in organic compounds. When you have double bonds in them, they generally tend to form. That's where you normally see it the first time. So here we will look at the geometry. In this case, there are 6 ligands. Therefore, it tends to form usually 6 coordinate bonds, which will result in an octahedral complex. That's what normally happens. But at the same time, the positions of the chlorines within the molecule actually has an impact on the color of the compound. That's the interesting aspect here. Many coordination compounds are brightly colored. Different coordination compounds from the same metal and ligands can give quite different number of ions when they dissolve, and this is what we are trying to illustrate here. And also by virtue of the position of the ligands, we find the color of these compounds are also going to be different. Werners theory. So Alfred Werner is a scientist who did extensive study and the behavior of complexes and the compounds, and he tried to explain them. So in order to do that, we can actually look at the same examples that we had seen in the previous slide. So if you look at these compounds, all of them, if you determine the oxidation number of cobalt in all of them, you'll find that the valency is going to be +3. In order to give you an example, for the first case, CONH36Cl3, there are 3 chloride ions. That is going to be -3 because 3 into -1. Ammonia is a neutral molecule, so the oxidation state is taken as 0 because hydrogen is +1. There are 3 hydrogens +3. Nitrogen has a valency of -3, so it's going to be 0. So cobalt +0 times 6, which is not counted, -3 is equal to 0, so cobalt is going to be +3. So you will find that the oxidation state of cobalt in all of these compounds is going to be +3, +3, +3, and +3, which means the primary valency, the common valency that we always talk about for metals, is what we have decided it to be by calculating the oxidation number. They all have the same value. And there is no need to explain how we should satisfy its valency because that's what we learned in ionic bonds. But at the same time, if you go to the third column, it says secondary valency, which is the coordination number. You'll find that in all of these cases, the coordination number is 6. In the first case, the single ligand, 6 of them. In the second case, 5 ammonia and 1 chlorine, making it 6. In the third and fourth case, 4 ammonia and 2 chlorines, making it 6. So the secondary valency is 6 for all of them. And this is what we are really trying to explain when a complex is formed. The primary valency and secondary valency together is taken into account. And therefore, there is violation of common rules. That's what we are seeing based on what we have studied earlier. So the last column is very obvious. So the number of the free chloride ions in the first case outside the coordination sphere, 3 chloride ions. In the second case, it is 2 chloride ions. Third and fourth, exactly the same formula, therefore 1 each. Werner proposed that the complexes have 2 kinds of valencies, primary valency and the secondary valency. The secondary valencies are also called coordination numbers, and they are written within square brackets, which we call the coordination sphere. The primary valencies are the common ionizable valencies of the central metal ion. So that's the fundamental difference between the 2 types of bonds that are formed. The primary valency, which is mostly ionic, and the secondary valency, they are formed by coordinate covalent bonds. So here is an example. We have a coordination number of 6. That's a secondary valency. 3 plus is the charge of cobalt, which is the primary valency. The 3 chloride ions, whether it's present within the coordination sphere or outside, it can satisfy the primary valency. So whenever you have negative ions in a complex, whether it belongs to the coordination sphere as a ligand or whether it's outside, doesn't matter. It still satisfies the primary valency all the time. That's something that you may want to bear in mind. The oxidation number of cobalt in this case is +3, therefore it is CO3+. So we have identified the primary valency and secondary valency merely by looking at the formula of the complex ion. That's what we have done at this point. Now we're going to look at some general properties that we see. Usually compounds are colored. Now again, the same example that I have taken earlier, a complex of cobalt with 2 chloride ions and 4 ammonia molecules. So this is the same compound. But if you look at this, the color of these compounds, they are slightly different. One of them is violet color, the other is green in color. And the difference that you observe is the position of the chlorides. The chlorides are adjacent to each other when the complex is violet, and in the second green complex is opposite each other. This is the cis and trans positions that we are referring to. So the empirical formula for the compounds on the left are the same, but the colors are different. Or we can generically write the formula of this compound as COCl3.4NH3. This is not the conventional way for writing the formula of a complex, but this is the empirical formula for both of these molecules. Now we can write the formula as we would for a regular complex compound using the coordination sphere, CONH3,4Cl2 and 1Cl outside it. So one of the 2 forms has 2 chlorines next to each other. So you can see those 2 chlorine atoms in the first compound, they are close to each other. The other has chlorines opposite to each other. So that's the fundamental difference. The position of the ligands actually influences the color of the complex. That's what we're really looking at here. So we should be able to explain why this happens later when we look at the d orbital splitting. This change in geometry of the 2 molecules leads to the difference in color of the complexes that have the same empirical formula. Metal ligand bonds. The bond is formed between a Lewis acid and a Lewis base. I did say this earlier. I'm just going to repeat it again because that's the foundation for explaining the bonding in complexes or coordinate covalent compounds. The ligands are Lewis bases because they have lone pairs of at least one lone pair which is available for coordination. They are called lone pairs or non-bonding electrons. The metals, which we call as Lewis acids, as empty orbitals, and transition metals, like you already know, they are generally colored. So most of the complexes that we see are from transition metals, which give us beautiful colors. So empty orbitals available for bonding with the lone pairs of electrons that are coming from the ligands is what makes it possible to form complexes. Now, you may have learned the periodic table. When you move from left to right in the periodic table, one of the properties is what happens to the size of the atom. The size of the atom tends to decrease, and this is because of the increased nuclear charge. And therefore, this has tremendous impact on the orbitals that are not completely filled. The size changes, and the energy required for actually having the electrons in them, and the excitation and de-excitation is what we're going to refer to as we move along. Now, one of the tests for the presence of chloride ions, if you actually did qualitative analysis, probably in grade 11, if you want to detect the presence of chloride ion, one of the reagents that we tend to use is silver nitrate. Silver nitrate, when you add to any chloride, forms a white precipitate, which is pretty stable. But white precipitate could mean anything. So many different compounds could have white precipitates. But one way to actually determine whether the compound, the white precipitate that is formed when silver nitrate is treated with sodium chloride, for instance, which is a double displacement reaction, is to confirm its presence by the formation of a simple complex that we see here. So on the right side, you have two ammonia molecules actually coordinated or bonded with silver, and this complex compound is actually ionic in nature. Therefore, silver chloride tends to react with ammonia, which is a very strong ligand, and tends to form a complex which is soluble in water. This compound, the formation of this compound is actually confirmation for the presence of chloride by a secondary test. So we use formation of complexes to detect the presence of certain metal ions or even non-metal ions in aqueous solutions by preparing suitable complexes having specific color and specific properties. So that's one of the things that you would notice, some application of complex ion formation. This is very straightforward. Just to tell you what we need here, we already have calculated oxidation numbers when we learned redox reactions. So in the same way, here I have a complex ion. Now what you will need to add to the information that you already have based on the oxidation numbers of elements, we are using ligands which have oxidation numbers too. Ammonia, for instance, has an oxidation number of 0. Water has an oxidation number of 0. Carbonyl group CO has 0. So there are certain compounds that have 0, and most of the others are the common oxidation states that you already know of. So in this case, this complex is a positive complex with a 2 positive charge, which implies copper has a 2+ charge. Oxidation state of copper is +2 because ammonia is having an oxidation number of 0, even though it's called tetramine copper to a complex ion. So you will be expected to calculate the oxidation number so that you can write the name of the complex. In order to write the name of the complex, you need to have the oxidation number, and we will include the name of the oxidation number of this element as Roman numerals in the name. For that reason, we need to know. So that's the way we calculate it. So you can reason it out. So I just took an example to illustrate that. So knowing the charge on the complex ion and the charge of each ligand, one can determine the oxidation number for the metal or the primary valency of the metal. That's what we are trying to do here. So we are looking at coordination numbers here. If we look at complexes where there are 4 ligands, in the 2 examples that are given here, you find the 2 possibilities for the geometry of the molecule. One of them is tetrahedral and the other is square planar. In both of these cases, you have 4 bonds, 4 coordinate covalent bonds. According to Werners theory, you know that if there are 4 bonds, the molecule is going to be tetrahedral. If the molecule is tetrahedral, it would have been straightforward. But certain of these complexes tend to form square planar molecules. And you should also be able to explain why this happens. That's an expectation. Okay. The second possibility is if you have the coordination number of 6, If you have 6 bonds, the hybridization is sp3d2, and SF6 is an example which you have already seen. So the same applies to even coordination compounds. If you have 6 ligands, they tend to form octahedral complexes. So this is a general statement. Some metals such as chromium and cobalt consistently have the same coordination number, 6 in the case of these two metals. The most commonly encountered numbers are 4 and 6. So if the coordination number is 4, the shape has to be either tetrahedral or square planar. And if it's 6, it's going to be octahedral. So that's a generalization that we can make based on the number of bonds that are present in these complexes. Of course, if you only have 2 bonds, then it's going to be linear. It's again very reasonable to make that statement, unless you have lone pairs which are not balanced out. Again, we already stated this. So the 2 most common geometries, we already know from hybridization. If it's tetrahedral, the hybridization has to be sp3. So it would be good to recall that information. And if it is square planar, it's going to be dsp2 hybridization. So those are some of the things that you would find. So to bear in mind, coordination number is 6, octahedral. Coordination number is 4, 2 possibilities, tetrahedral and square planar. Polydentate ligands. So some of these ligands, they have 2 or more donor atoms, or it can donate 2 lone pairs or 4 lone pairs or 6 lone pairs coming from a single molecule. That's what we mean by polydentate ligands. Just because of the number of electron pairs that can be donated, they are also called chelating agents. These complexes are actually pretty stable too. One common example is ethylene diamine. Is a traditional trivial naming system here. So the molecule is an ethylene molecule with 2 ammonias on either side. So it can be written as NH2, CH2, CH2, NH2. This is the molecule. So nitrogen, wherever you see nitrogen, when it is showing trivalency, you'll find that it has a lone pair. So that is something that you may have to fix in your mind. Any compound that contains nitrogen, where it exhibits a trivalent bond nature, it should also have a pair of electrons to satisfy the octet based on what we already know. So for that reason, the 2 ammonia or nitrogen molecules in ethylene diamine has 2 lone pairs. Therefore, it can allow these 2 lone pairs to be coordinated because the molecule is reasonably long, and it can change its direction, and it can actually coordinate with a metal with a central metal atom. And for that reason, ethylene diamine is actually used very frequently to prepare a number of complexes. Ethylene diamine, the name is pretty long. So in order to write it within a coordination sphere, we use it as En. The short form for representing the ethylene diamine is En within a bracket. So we normally don't write ethylene diamine, we merely write En within the coordination sphere to illustrate this polydentate or bidentate ligand. So if you have 2 pairs of electrons, it is bidentate. If you have 4 pairs of electrons, it's going to be tetradentate. So here is an example of a complex of cobalt with 3 ethylene diamine molecules. The 3 ethylene diamine molecules can provide 2 times 3, 6 electron pairs. Therefore, it represents a shape similar to the one that we had seen earlier, an octahedral shape, but the electron pairs are coming from the same molecule, and that's the only difference here. EDTA, I'm sure you have come across EDTA earlier. Ethylene di. So here we have ethylene diamine tetraacetate. It's ethylene again, or ethene, and we also have 4 acetate ions actually attached to it, and 2 nitrogen atoms altogether makes the number of pairs of electrons that it can donate as 6. So this may be a structural representation of it, of EDTA. EDTA has the ethylene diamine in the central portion. So if you actually go to this region over here, you'll find that, so this is the region that I'm talking about. If you go to this region, you'll find the ethylene molecule diamine, so the 2 amines, and the 2 hydrogens on each nitrogen is actually replaced by the acetate ions that we have. 1, 2, 3, 4. 4 acetate ions that are present there can actually are the ones that are attached there. So we find the oxygen over here can give an electron pair. Same is the case over here, over here, and over here. 4 pairs of electrons coming from the negative oxygen atoms that you have. 2 pairs of electrons, one from over here, this nitrogen, and the other from this nitrogen. So the simplified version is over here. And so you can use ethylene diamine tetraacetate, which is otherwise called EDTA. Now, one of the important applications of EDTA is removing the hardness of water or estimating the hardness of water. Water can be soft water and hard water. Hard water means it contains magnesium and calcium. So this is a very good chelating agent where you can actually bind magnesium and calcium with EDTA and estimate the hardness of water. And for that reason, this is a standard titration that is available in chemistry labs for the determination of hardness of water. So again, this is another polydentate ligand where we have 6 lone pairs coming from a single molecule. This is a general statement that I made earlier. Chelating agents tend to form more stable complexes. We can calculate the equilibrium constant for the complexes, and those values will be reasonably high if the ligands are actually bidentate, tetradentate, or hexadentate ligands. Here are some examples. Monodentate ligands, which has 1 pair of electron. We had seen aqua and amine, water and ammonia, fluoride, chloride, cyanide, thiocyanate, hydroxide and nitride. They are all molecules that can donate a single pair of electron. So they are called monodentate ligands. Bidentate ligand, we had already seen En or ethylene diamine, and the formula and structure is written here. Bipyridine, again, that is benzene with 1 carbon atom replacing nitrogen replacing one of the carbon atoms will give you pyridine. A bipyridine complex is again a very good ligand. Like I said, nitrogen, whenever it's bonded with 3 bonds, a single and a double, it also has a lone pair, makes it a very good ligand. Oxalate ions. Oxalate ions comes from oxalic acid, if you know, H2C2O4, or it's a dicarboxylic acid again. Carbonate ions again can be bidentate ligands. And polydentate ligands, again, EDTA is an example, or triphosphate ion is a common example. Detergents contain sodium phosphate ions present in them, and that's good to remove hardness of water. When you buy detergents, and especially you use detergents when you wash clothes, because water can contain calcium and magnesium, or hard water, if you're using it to wash clothes, it takes up a lot of soap. And soap, when it reacts with calcium and magnesium, forms insoluble precipitates. So how do we deal with it? We use detergents which contain trisodium phosphate, which actually complexes with the species that causes hardness of water, and thereby forms soluble substances that will not interfere with the washing process. So this is the formula for the triphosphate complex that is formed, that is present. You must be familiar with this, so just to give you a practical application there. Now we're going to look at some general common examples of molecules that contain or are complexes that are present in living organisms. Now, if you look at this, the central portion, the ring system is kind of common, but the peripheral atoms keep changing, and you have a number of complexes that have metals in them. And here we have magnesium, and so it should be self-evident what this complex is. This is actually chlorophyll, because leaves contain chlorophyll, and chlorophyll is actually an organometallic complex which involves magnesium in it. Again, you have this is a structure that I said, which is a common portion, the porphyrin, which would be the part that actually becomes the chelating portion, attaching itself to the metals. Again, hemoglobin contains iron, where iron is actually coordinated with the ring system. Again, that's again a biomolecule. Many vitamin B1, B2, B12, you'll find that they contain cobalt in them. They form complexes again. So some practical application of chelating agents would be present in all of these. That would be general reading that you should be doing, and some applications or presence of complexes in real life and biomolecules. We will take a quick look at nomenclature of complexes. Like in ionic compounds, we always name the positive part of a complex first, followed by a negative part. With the difference being in a complex compound, the positive part and the negative part can be complexes, or we can have the positive part just a metal and the negative part a complex, or the positive part can be a complex and the negative part can be a negative ion. Usually the name of the metal or the positive part is actually what we name first, and we need to know if it's a complex, the oxidation state has to be found, and we have to include the oxidation state of the central metal in the complex while we write the name. If the complex is a negative ion, which means it's the second part of the molecule is a complex, it will contain a metal, and in order to differentiate and make it very evident that that part of the complex is negative, the name of the metal usually ends in ATE. For instance, if you have nickel as a complex, as a metal in a complex which is negatively charged, the nickel part will change into nickel 8, followed by the oxidation number. We will write a couple of examples, so we'll just state the rules first. The basic protocol in naming coordination compounds is to name the ligands attached to the metal as prefixes before the metal name. So within the coordination sphere, you have a metal. First, you will name the ligands, and you will indicate the number of ligands that is present. If more than one ligand is present, we go in the alpha order for the name of the ligand, not the number. So we will look at a couple of examples. Now, one point to note, when we talk about bidentate and tetradentate ligands, for instance, ethylene diamine, if the ligand already has a number associated with its name, for instance, ethylene diamine, there is a di within the name. And if you have two of them or three of them, you do not want to use diethylene diamine. So in such cases, what we do is, if the ligand, which is a bidentate, tridentate, tetradentate, then if two of them are present, we say it's bis ethylene diamine if there are two of them, or tris ethylene diamine if there are three of them. So we tend to use a secondary numbering system if the ligand already has a number like di, tri, tetra within it. So that's something that you may want to note. Otherwise, it's straightforward naming. Here are some common names of ligands. The first column is a ligand. Azide or N3, that's a common name with a formula: bromide, chloride, cyanide, fluoride, hydroxide, and carbonate. And on the second column, what I've done is I've given the names of the ligands as it would be written within a coordination sphere. So if you have N3 within the coordination sphere, we call it as azido. Bromine will become bromo, chlorine will become chloride, will become chloro, cyano, fluoro, hydroxo, carbonato. Similarly, again we have more oxalate, oxide will change into oxalato, oxo. Ammonia changes into amine and water changes into aqua. We have seen that earlier. Carbon monoxide changes into carbonyl, ethylene diamine we had seen. So you may want to familiarize yourself as to what will be the name of the ligand when it is placed within a coordination sphere. So here is an example for you. We're just going to apply the rules that we have. So if you ionize this complex compound, it gives you CONH3 within square brackets and with a charge of 2 plus 2 chloride ions. So this complex part is positively charged. That's very important. So we have to name the positive part first. So in this case, let's write the example, and within the complex you have 5 NH3 ligands, 1 chloride ligand within the coordination sphere. The oxidation number of cobalt is +3 in this case, and we have an anion which ionizes to produce 2 chloride ions. So if there are 5 ammonia ligands, it becomes pentamine. Penta is 5, so pentamine indicates 5 ammonia ligands. There is 1 chloride ion that becomes monochloro. The ending is chloro, as we had seen earlier. Cobalt has an oxidation number of +3. So in Roman numerals, we should include the oxidation number of 3. And that's about it that we need. And finally, the whatever is outside, we don't have to actually number it. We will simply say it as chloride, just like in ionic compounds. So the name is pentamine monochloro cobalt 3 chloride. That's how you can name a compound. If this was a negative complex, then it would have been cobaltate. So in this case, it being a positive complex, we will merely call it as cobalt. But we have to indicate the oxidation number, because without the oxidation number, we will not be able to generate the formula of the compound from the name. So that's the reason we include that. It's just like writing the Roman numerals in multivalent compounds, which you have done in naming of compounds earlier. Isomers, same unit. Iso means same, mer means unit. You're kind of familiar with that or that word. So if you look at isomers, they generally have the same formula but different properties. Isomers can be classified into structural isomers if they have different bonds, and the coordination sphere isomers and linkage isomers are examples of structural isomers. We will see an example of linkage isomer here. Then we have stereoisomers. This arises due to the different spatial arrangements of the bonds within a molecule. That leads to two kinds. One is called the geometric isomer and the other is called optical isomer. Probably you would have seen optical activity in biological compounds, so you must be familiar with the concept of optical activity. So that's a general statement. Isomers have the same molecular formula, but their atoms are arranged either in a different order, that is structural isomers, or spatial arrangement is different, then it gives rise to stereoisomers. So here we have an example of a complex in which one of the ligands is NO2. On the left side you can see a compound that is having a particular color, and if you look on the right side, the formulas of both of these compounds are exactly the same, but one has a slightly deeper color than the other. So the difference that we notice here is one of the ligands is NO2. NO2, the in the complex on the left, the nitrogen is attached to the cobalt atom. And on the right, the oxygen of NO2 is attached to the cobalt atom. That makes all the difference in terms of the color of the complex that we have here. So the isomer on the left is called nitroso isomer, where nitrogen of NO2 is attached to the cobalt. And on the right, you have oxygen of nitro NO2 group, which is attached to the cobalt, which makes it nitrito isomer. So we can differentiate which atom is actually attached to the central metal, and there is a distinct property difference, or the intensity of color is going to change, or we have different colored complexes just because the atoms attached to the central metal in the complex is different. Because the linking atoms are different, they are called linkage isomers. So the same ligand, but the atoms that are linking or providing the electron pair for the molecule is going to be different, and thereby you have different properties for the products. Structural isomers. So here we had seen a number of examples in the first few cases where some isomers differ in what ligands are bonded to the metal and what is outside the coordination sphere. These are called coordination sphere isomers. Merely by changing the ligands from within the coordination sphere to the outside, we get this arrangement, and therefore they are referred to as coordination sphere isomers, and it's a structural isomer. So here we have CrCl3H2O6. This is a conventional way of writing the basic generic formula. And if you write the formula using the coordination sphere and Werners theory, you'll find the compound Cr, or hexaquo chromium 3 chloride, is violet in color. And again, if you look at this compound, there are 5 water molecules within the coordination sphere and 1 chloride ion inside. The color changes, it changes to green. And one of the molecules of water is now outside the coordination sphere. Now you find that by changing that combination, or the ratio, or 2 chlorides within the coordination sphere and 2 water molecules outside, again it gives you a different complex. And the color is also different. It's green, but probably the wavelength of these colors, the intensity is going to be slightly different. So the whole idea is structural isomers are coordination sphere isomers, where the ligands are changing positions from within the coordination sphere to the outside, or from the outside to the inside. So that change is what the empirical formula doesn't change for any of these. That's what we are emphasizing here in this example. Stereoisomers, again, we had seen this earlier. Cis-trans isomers, I did talk about the position of the chlorines in the earlier case with an illustration. So if they are on the same side adjacent to each other, they are called a cis isomer, and if they are on the opposite sides, they're going to be called trans isomers. Again, geometrical isomerism, which you have already seen or you must be familiar with, you can use that as a basis. The 2 chlorines and the 2 ammonia groups are bonded to the platinum metal. So here we have a coordination number 4. So the molecule has 2 chlorine atoms on the same side and ammonia molecules again adjacent to each other. Then we have the cis isomer. And if you find them to be on the opposite sides, then we have the trans isomer. And that's what the stereoisomer for cis-trans isomerism would look like in a complex molecule. So trans would be usually opposite side, cis would be on the same side. Here, stereoisomers with reference to optical activity. That's what we're looking at here. Your hand is chiral, which means your left hand and right hands are mirror images of each other. If you put your left hand on the right hand, they're not superimposable. That's a statement that we tend to use. So materials that are not superimposable, but they have similar molecular structure, they are supposed to be optically active isomers. Now, optical activity has to do with the presence of an asymmetric structure or asymmetric atom within a molecule, which we call a chiral molecule, a chiral atom. And that's what we're really looking at. So lactic acid, we have the D-lactic acid and the L-lactic acid that you're familiar with. One gives you, and if you take lactic acid, you have the dextro-rotatory form and the levo-rotatory form, which means if light or polarized light is passed through an aqueous solution containing a compound that can exhibit what we call optical activity, we find that compounds that are related to each other as object and mirror image, they will rotate the plane of the polarized light in the opposite direction. So that's what we refer to as optical activity. So if you take lactic acid that is giving positive rotation and lactic acid that gives you negative rotation, they are two different types of optical activity. Interestingly, if you take lactic acid which has a mixture of both of these and you crystallize them, you will get left-handed crystals and right-handed crystals. You can observe them under a microscope and actually separate them, and you'll find that they will have opposite optical activity. So it's just like your hand, left hand, and if the mirror image looks exactly like your left hand, but it is not superimposable. What you mean by it, if you put your left hand and put your right hand over it, your thumb is going to be facing the opposite direction. They're not superimposable. So there are molecules that have this property, or molecules that are asymmetric, or there are atoms that are asymmetric within a molecule. So if that is the case, if a molecule has an asymmetric mirror image, then they will show optical activity, and these would be called optically active isomers. So you can see optically active compounds in coordination compounds and also in a lot of organic compounds, sugars and all of those things. They have asymmetric centers or chiral centers, and these are based on the symmetry of a molecule. So if you look at the elements of symmetry, any object that is symmetrical will not be asymmetric. If you has any, like the plane of symmetry, rotation symmetry, all of those, it will not show any kind of optical activity. If you take methane molecule, it's a symmetrical molecule. But if you replace all the 4 hydrogens by 4 different atoms, the carbon atom becomes asymmetric. And then if you make a mirror image of it and a structure similar to that, you'll find that those 2 compounds will show opposing optical activity. So the important aspect here is compounds that have the same molecular formula, but spatial arrangement is going to be different. They are related to each other as object and mirror image in terms of the distribution of atoms in space. Then they will represent different optically active properties. So again, it's a stereoisomers. Isomers are compounds that have the same molecular formula, similar units, but they will have different properties. So that's what we are referring to here. So we can have isomers for these complex compounds where you should be able to identify stereoisomers coming under geometric isomers or optical isomers, which we had seen the different examples. Now, this is a term that we tend to use, enantiomers. Compounds that are related to each other as object and mirror image are usually referred to as enantiomers. So optically active compounds are either asymmetric molecules or have at least one chiral center, we said. Now, enantiomers are compounds that are related to each other as object and mirror image, and they will both exhibit optical activity. One will be the opposite of the other. So we can have enantiomers in complex compounds too. Here is an example. Explaining color. So I do not know how many of you have time because it's already 1 hour. So let's see if you can stay, I can finish this part. Explaining color and crystal field theory. So here we're going to look at some aspects that we already learned. This is the d orbital. dxy, dyz, xz, x squared minus y squared, and dz squared. And they are called degenerate orbitals because they all have the same energy. So energy keeps increasing from bottom to top. They are degenerate orbitals. So if you have these metal with an d orbital that is partially filled, and if you have ligands approaching the molecule, we will call it an octahedral field. The d orbital loses its degeneracy. It splits up into two. Now, if you draw the orbitals, you'll find dx squared minus y squared and dz squared. The orbitals are along the axis. So the repulsion when these electron pairs approach the d orbital will be higher for the dx squared minus y squared and dz squared because they are along the axis. Whereas the xy, yz, and zx, they are in between and they will have a lesser repulsion. Therefore, there will be a difference in energy, degeneracy is lost, and then if you have electrons, they fill into these split orbitals, which we call T2g and Eg, and this value, you'll find that the energy difference is considerable, and the energy required for promoting an electron from the lower level, dxy, yz, or xz, to an x squared minus y squared, usually is available within the visible region. So if white light is provided, the electron can actually transition from the lower level, which is a T2g level, to the Eg level. These are spectroscopic symbols, term symbols. So the T2g level of orbitals, the electrons are at a lower energy level, and if you actually subject it to some kind of radiation, the electrons in this level can absorb the energy and move to the higher energy level, that is the Eg level. So imagine you have a beaker containing some transition metal complexes. If you pass light into it, what will happen is the electrons in the lower level, T2g, can absorb some kind of radiation wavelength, and then the electron can move to the higher energy level at the Eg level. So what happens to the light that is coming out is devoid of a particular wavelength. Therefore, the solution will show the complementary color, and that's how we see color when transition metals are dissolved in water, especially when you have incompletely filled d orbitals. So this is what we refer to as the crystal field split. So every time a d orbital undergoes a bonding with complex with the ligands, it tends to undergo splitting. It forms an octahedral field, and then you can see energy is absorbed for the transition that causes the substances to be colored. So the important aspect is degeneracy is lost. They're split into two, and this is what we refer to as the crystal field split. Now let's take an example and see how this works. So here we have complexes of chromium. The first one is CrF6, second one is CrH2O6, CrNH36, and CrCN6. If you look at the delta E values for all of them, it keeps increasing. So you have the fluoride or the fluoro complex and the cyano complex. Cyano complex has the highest crystal field split. So if you want to compare the wavelength absorbed by CrF6 and CrCN6, you'll find that the CrF6 absorbs the longer wavelength and CrCN6 absorbs the shorter wavelength, which means E is equals to hc by lambda. You know the equation, relating energy and wavelength. They are inversely related. Shorter the wavelength, higher the energy. Therefore, you'll find a complementary color is shown by CrCN6, which will be yellow, and it will be green for CrF6. So the crystal field split depends on the metal, depends on the ligand, and that difference will make a difference in the color exhibited by the aqueous solution containing these transition metal complexes. So reading about crystal field theory and trying to use it to predict the color of complexes is something that you should be doing. And you can see the practical application of it. Why a small change in the ligand in the coordination sphere can bring a small difference in the wavelength absorbed by the electrons within the d orbital. So that's a very quick and short review of the complex. I have one more lesson for you on complexes, that is explaining the formation of the octahedral complexes and the tetrahedral complexes. So probably we'll do that one of these days. That's it from me. If you have any questions, don't hesitate to ask me. So we will stop it for today. And one more lesson I do have for this topic. Okay guys, have a nice day and stay safe.